Good afternoon, and thank you for inviting me, Cynthia and Kunal. I'm very new to this community. Not so new to the area though. I heard about differential privacy a little over a year ago, 15 months ago. So I'm enjoying it. This is joint work with my student Chuan and my colleague Sevung Oh. Sevung couldn't be here. He's giving a colloquium talk at Stanford around now. All right. Cool.
You need to play. Hit play.
Need to play? Well, that works. Okay. I'm new to differential privacy, but I work in an area called information theory, which is the following. Okay, so it's among many things. It's the following, where it's basically the mathematical theory behind communication. So you have some data, and that needs to be somehow communicated from one point to another point. Along the way, you have a physical channel and some physical resources. So this is like the underlying mechanism behind all data transfer, wires, wireless, whatever. I would like to say that there's a various connection here. So the thing is that what you get is not what you send. There's a channel in between, and that's random, and that's usually nature. So we have statistical models, and we just work with them. Sometimes we work with worst case models too. And the designer or the engineer gets to decide the encoding and decoding functions. And the goal end to end is to have small error probabilities. Privacy, I look at it through these lens of information theory. At least differential privacy looks, it has similar block diagrams. You have data, and instead of encoding, you think of it as a query, which I've just put down as nature, but it could be something else, like what the database is queried with. So query is something, let's say I call it nature. Sanitization is what I get to design. Adversary works tries to do the best decoding and tries to learn something about the data. The thing is, it has similar block diagrams. Different things are getting designed, but in privacy, we want large error probabilities. There's another difference, which is in communication, I think of it, information theory, I think of it as multi-hypothesis testing. So I think of data as many possible values, and I want to get all the exactly right. So it's a multiple hypothesis testing problem. Differential privacy, though, works with user being there or not. So it's really binary hypothesis testing. I should say that it could be any user, so it's many binary hypothesis testing. So it's multi-binary hypothesis tests. Okay, and this is small error probability, large error probabilities. Because it's binary hypothesis testing, there are only two types of errors. There's false alarm, misdetection, type 1, type 2. And throughout this talk, I'm going to plot these curves. They're all, for the statistics community, this would be an ROC curve, almost, except instead of plotting 1 minus probability of misdetection, I'm plotting just the probability of errors. And differential privacy, the approximate differential privacy says that both errors, false alarm and misdetection, should be large enough. I'm going to use this diagram will be throughout pretty much in nearly every slide. So let's get the notation right. So I'm just plotting error probabilities. There's a binary hypothesis test. A user is there or not. And as long as the error probabilities are in this red region, you say the mechanism is epsilon delta differentially private. Notice that this height is delta. I guess this intercept here is delta. The slope is e to the negative epsilon. Okay, so that's the parameters epsilon and delta. This is not exactly how, of course, differential privacy was defined. So I should just say quickly, when delta is 0, you just have this triangle type of a thing, as opposed to a pentagonal structure with delta. All right. This is not exactly how it was originally posed. It's posed as a ratio. The likelihood ratios are between e to the epsilon and e to the negative epsilon. Or the log likelihood ratios are between epsilon and negative epsilon. But it's known that equivalently it's just, in fact, it's an exact equivalence. This is implied, but it's also true the other way. And so it's really a very tight connection. The reason I want to say this is because information theory is all driven by operational connections to hypothesis testing. It's a very critical step. Information theory is a mature area. I don't think this is polemic, so I think it's safe to say this. It's been around for a while, and it's been successful too. And among many things, one of the successful things that theory has done is to identify extremal limits to how well you can do the encoding and decoding, and hence get to fundamental benchmarks. In particular, we are interested in the communication context, we are interested in the maximal rate you can do reliable communication, arbitrarily reliable communication. It's called capacity of channels and so forth. So, I mean, understanding the extremal limits has many benefits. One of them is to set fundamental limits, lower bounds. It also provides insight into practical schemes that get close to achieving it. And much of these results are derived through a lens of hypothesis testing. So this is the so-called operational interpretation, and it brings value, mostly because it gives insight to how you're doing the proofs, but also because they're just technically strong. Data processing inequalities are strong. Okay, so that's the information theory story. And in this talk, I would like to do a similar program for differential privacy. I would like to identify extremal mechanisms in this case, hence setting fundamental lower bounds, all along the way using the lens of the binary hypothesis testing operations. Nothing new by say, I mean, this seems interesting to anyone. And so I have sort of three types of results to say in this context. One, I'll propose an extremal mechanism. I'll call it staircase to get started. It's a noise adding mechanism, so it's got real numbers, it's got an algebra of topology of real numbers or integers and stuff. So you can add things. And furthermore, it's only data independent. Let's get started. Once I try to understand what's happening here, we'll derive composition theorems. They're exact. And once I even understand that, the real goal is that I'll understand why this was actually a universally optimal mechanism. And so there's a notion of an abstract staircase mechanism. This is neither noise nor is it adding, but the intuitions are all right here. And it's really the right mechanism. It dominates every other mechanism in a strong sense. I'll precisely define what the sense is. Okay, so that's the goal for this talk. Yes?
Optimal noise adding, is this for one query or for multiple queries?
I'll be precise if you are. Just give me 1 minute. Yeah. So I'll be precise about all these statements. Okay. So I just want to get started. So I'm new to the community in the sense, so I look at the state of the art in the sense what are mechanisms people use. Well, I looked at Laplacian noise. So that's exponential mechanisms both-sided. I like that. Gaussian noise. So it's rare to go through an information theory paper without Gaussian noise. So we like that. I understand it reasonably well. And but there aren't any exact optimality results. So I think about it. And I look for other mechanisms just around in the literature. And I find this one, which is for integer valued queries, not real valued. These are integer valued. And let's specifically fix count queries where the sensitivity is just 1. And then there is a mechanism which is to add geometric noise. And this one has optimality property. It's universally optimal in a certain cost minimization framework over sort of most interesting costs, but it was sort of Bayesian prior on the input. There's no operational meaning in the sense that this is a sort of a functional analytic proof, decision theoretic proof, which is good. But I'll just point out that since I look at the lens of my binary hypothesis test, the likelihood ratios are between epsilon and negative epsilon. But for this particular mechanism, they're only the extremes. Okay, so let's just keep this in mind. We'll think about it as we go along. So I thought about this staircase mechanism, and so we thought about it, and here's a generalization. The same integer setting, one single count query. So to answer Cynthia's, just one query. The same setting as before, one query. And this time I allow sensitivity more than 1. And I also consider a worst case inputs. So there's no prior on the input. It's worst case cost. Worst case over the inputs. And I would like to minimize the worst case cost. And we look at it and we find the universal mechanism. It's not geometric anymore. It's if delta equals 1, it will become geometric. But otherwise, it has this staircase shape. Okay, that's the name, staircase. Again, if you look at our proof, there's no operational interpretation, operational at least intuition. It's sort of functional analytic proof. And I'll just point out that among all, again the log of the likelihood ratios are between epsilon and negative epsilon, but this time it takes only 3 values. The 2 extremes or 0. Okay, yeah, Sashu.
What is the cost?
I haven't defined it, so that's the next slide. Thank you. So
can you explain that the graph in more detail? What is?
So this is the PMF. So I could have plotted, I guess, the geometric noise. Sure. The geometric noise would have been like this. It takes only integers, and like this. This one has flats, and then it jumps down. Flat, jump down.
And the colors?
Okay, so there is a coding for the color, and 2 more slides. How about that? This is a PMF of the noise, the probability mass function, and if you want to think of it as probabilistically, it's a geometric mixture of uniform random variables. These are uniform random variables, and where they are is geometrically mixed. It's a discrete geometric mixture of discrete uniform random variables.
And here delta is less than 1?
No, these are integer valued, so delta can never be anything less. So delta is an integer. These are all integer values.
So this is delta equals 5 or something?
In this particular case, 1, 2, 3, 4, 5. Exactly. And the colors have a meaning, indeed. Hang on for 2 more slides. And Sasha asked about the cost. So this is the right mechanism, universally cost minimizing mechanism for all these kind of costs. I look at, these are noise adding, so these are not data dependent in general, so they're very special of type where I add noise. And I look at the cost, which is any function of the noise and the average of that. And any function, well, not any, but anything sensible, that means it's sort of symmetric around 0. That's the symmetric part. And then there it's more noise means more cost. So it's monotonically increasing. This setting is very similar to the delta equal to 1, the GRS paper. Okay, very similar. In fact, the same setting. The only difference really is that they were doing Bayesian setting. This is worst case. And this is just one query. At this point, just integer value. This makes sense?
So it's one query and data independent.
And data independent. So we'll get to all of that.
If I remember correctly, the GRS paper didn't assume data independent.
Exactly. So Adam is totally right. So the GRS proof worked for data independent. And so it was true, it was a universal one, even if you allow data dependence. Turns out, if you make some technical assumptions among the class of such functions with more delta, it's also true, but that's, at this point, let's not get there. So that's a good point. Thank you, Adam.
So just that I will follow you. What exactly is delta? What do you mean by delta here?
When delta equals 1, oh, I see, sorry. So we need to understand that part. So delta equals 1, delta is sensitivity. And this is global sensitivity. And 1 means it's a count query. So having a user or not can only change the value of the query output by 1. And these are integer values.
Sorry?
Thank you, Adam. That's true. This is an important setup. Is this clear? This is a probability mass function of the noise. The total thing sums to 1, so it's really a PMF, probability mass function. This is discrete random variable, so it's T. Okay? And this is the setting in which it's universal. It's data independent, noise adding. If you put some technical conditions on the class of data dependencies, yeah, so we can talk more, but so let's move on. Okay, so I won't say that. The paper has more details. I could also think about real valued, and there is a natural generalization to go from integer to real valued, and it sort of looks like this. Again, there's a color coding. I'll come to it in, I said 2 slides or maybe 3, okay? So it's a generalization, and this time this is a PDF, probability density function. Okay, so here's how it looks like. So this is a closer look with all the colors in full display. Every width, every color has width equal to delta. So first thing you see is that this PDF is periodic. There's some periodicity property, and every color has width exactly delta. So it's periodic with period delta, except for sort of the starting point. You jump at a certain place. I call this fraction gamma. Apart from that, it's periodic with the width delta. And the jumps are always exponential. So that's the exponential discrete random variable. It's exactly an e to the negative epsilon jump from step to step. So the colors really represent where you first start off with, and that's this fraction gamma, and that's some number between 0 and 1, and that you get to tune as a function of your cost, based on your cost function. Okay, you get to tune this gamma. So I was kidding in some sense, in the sense that I cheated a little bit by saying this is the universal one. Actually, it's not it's a family of universal functions, one of which you have to pick based on the cost function. But it's parameterized by just one number between 0 and 1. The whole family is parameterized by just one number, between 0 and 1. So if you can look at so here's a special cost function, which is the magnitude of the noise, like the magnitude. And you can explicitly calculate, I see. So I said I have to tune gamma based on the cost function. But for special cost functions, you can actually solve it by hand. It solves a certain functional equation. You have to solve a functional equation in gamma. But as long as your cost functions are polynomially expressible, then you have to solve a polynomial equation in gamma. Yes, Sasha.
The first result had this property that you can add noise from a geometric distribution, and then I can come and based on my cost function, I can do some post-processing. So what you're saying is that this is not happening here, like you have to know my cost function and add noise based on
okay, that's true. I'll say a little bit more about universality of gamma too. So I'll have just a bit more to say. Good, that's exactly right. I need to pick gamma based on the cost function. You can pick universally and you'll pay a little bit cost, so I'll say just one slide. How about that? I'll say just a bit on that. So let's look at special cost functions like magnitude of x, and you can explicitly solve for gamma. There's some simple formula for it, and you can find a closed form expression for what is the minimum cost, and you can compare it with the Laplace one, and more or less for high privacy they look very similar. The multiplicative gap is close to 1, additive gap also goes to 0 even as epsilon goes to infinite, 0. Low privacy though, it's exponentially different. So this looks like 1 over epsilon, that looks like e to the negative epsilon. Low privacy may not be an interesting regime to operate in, but that's what the results are. So if I want to say in one sentence, low privacy costs exponentially less. Same thing with variance. I put down theta simply because there's a formula, it's just a bit too long to write down, but this is again a closed form expression. But qualitatively the same thing. The gap is small, and in high privacy, but in low privacy there's an exponential improvement.
Can you just give me a sense of scale, like when you say high privacy and low privacy, like?
Yeah, there's a knee of the curve.
What's the first value of epsilon for you save a factor of 2 or something?
No, in fact, very much. In my earlier slides, I even had some figures plotting the variance as a function of epsilon. Somewhere around 1.5 to 2, epsilon around 2, the knee of the curve sharply changes. And at that point, it just the variance dramatically starts reducing for the staircase mechanism. Somewhere around 5, I thought it was a factor of, okay, maybe I shouldn't speak. About 10. Yeah, okay. We have a paper, so we can look it up. In another version of the slides, I had those graphs. So Sasha has asked about gamma, and Cynthia mentioned what that color coding is. So there is a certain gamma star which depends on the cost function. I can say a few things. At low privacy, it should look like just pretty much 0. So you can just shrink it down. At high privacy, it should look like half the sensitivity. So just jump at exactly half. In general, I have a... Oh, I didn't put the universal down. I see. Okay, so in our journal version of the paper, there is a guess for gamma. It looks like half e to the negative epsilon. between 0 and half. And there are properties that say that that's a universal guess. You guess it once and for all. And there's a theorem about how good that works. Okay, so.
You said a half in the epsilon. What did you say?
You've picked gamma to be half e to the negative epsilon. It's a heuristic guess with certain properties. It meets these two conditions. And basically, the gamma star depends on the cost function in a functional way. It has to solve a fixed point functional equation. And you just try to understand unique sort of universal solutions to this fixed point equation. And so we can discuss that. But the hint is really this. Okay, so this is something I do want to point out, that among all the possible choices of the likelihood ratio, it really just takes on 3 values. So if the pairs are here, then the ratio is exactly 1, and then the log likelihood ratio is 0. If these two are the pairs, then the ratio is e to the epsilon, or depending on which way you pick, so those are the extremes. So it really takes only 3 values. And there's something about it.
So is it an intuition for where this is almost true for the Laplace noise, right? So if the variance is large, if 1 over epsilon is large, if epsilon is small, then most of the time you're in, if you're comparing 2 shifted copies of the distribution, they differ by exactly e to the plus epsilon or e to the minus epsilon. There's some probability that you get a number close to 0, and then the likelihood ratio.
But it's always a smooth function, right? The log likelihood ratio will be a smooth function for when you add Laplacian noises. It will be a continuous function. You'll have the whole range.
No, you're right, but it almost never. Yeah, okay, it doesn't matter.
It could have a shape. I'm not denying that.
I guess the point I was making was just that most of the time, meaning with probability, I don't know, 1 minus epsilon ish, it'll be that the log likelihood ratio will be either.
You mean the probability on the data, like you put prior on the data, or?
No, over the
coin flips in the Laplace noise.
Just saying,
it could be close. Are you saying it's flat, or
between the towers? Then you've got exactly the.
Okay, you know what? I don't want to stop you. Just keep going. That's fine.
Yeah, you're doing great. Keep going. I love to talk.
I'll ask you that.
It's not discrete, though. I just want to say that.
Right.
Maybe I'm leading you on, but there's something about this, so we'll talk about it. This is the thing that I found. So it's sort of a canonical result in that sense that. You can apply the Laplacian noise wherever you think of it as noise adding. You can go at the staircase mechanism, and for nearly every case it works, and performance just improves because the costs are sort of universal. And the improvements really come only at low privacy regimes. Okay, moderate to low, and Aaron talked about it, so we can look at exactly what numbers we want, depending on what numbers you like for epsilon. If epsilon was 5, I think that's what he said, then maybe this is definitely worth doing. But epsilon 5 is too large, then maybe not. Okay. There's 2 limitations, though. Okay, so among other things, there's 2 limitations. One, there's no intuition. Intuition is a fuzzy thing, and different communities treat it differently. In the community I come from, we really need intuition. We want it. We really value it. The reason is this intuition helps us generalize the results. So you could say this is special, this is noise adding, data independent, low privacy, high privacy, but to really generalize, we need intuition. We need to know why this is working. So in other words, I want to be able to do data dependent, query dependent mechanisms. Abstract, sometimes they're not even adding. I want to understand it. So that's really the reason to want that intuition. Along the way, of course, you never know what else you discover when you try to go for intuition. Okay, so how do we get this intuition? The intuition has to come from the hypothesis testing thinking point of view. And along the way, I gave some hints. So what values it's taking. So let's keep that in mind. So I go plot the false alarm misdetection curves for the mechanisms I have here. They're always within the triangle, remember, because they have to be epsilon 0 differentially private. In the very first part of the talk, I said it has to be inside this. So any curve you have has to be inside this triangle. That was the original setup. So you plot Laplace, it looks like this. You plot the Gaussian, Well, Gaussians are never epsilon 0 differentially private for any epsilon, and indeed, no surprise, there is no triangle that can contain this blue line. You can never fit a triangle that completely covers it. So you always need a little bit of slack here and here. Okay, so this is all known stuff. You plot the staircase. Staircase ROC curves look like this. It follows this line, and then there's a 45-degree line, and then it follows here.
Can you make it exactly go along the triangle?
Yeah, okay, so that's our next slide. Ideally, you want it to go exactly along the triangle. If you do that, then your mechanism is somehow doing just the right thing. Using as much flexibility as I have for my privacy and doing no more. In some sense, these are doing extras. All these are doing extra, more than your requirement. Why do more? I mean, you want to be as useful as possible means you want to have as small error as possible. So you want to do just right. You want to hit the triangle exactly right. These things are too complicated because for several things one of the things is that there are multiple query outputs, any integer valued or any real valued. Too many binary hypothesis tests. I was plotting only one pair and too many things going on. So let's try to simplify and look at just one special case. This is interesting in its own way. This is let's say the query output is just binary, yes or no? Only two values. There's a natural mechanism which is randomized response going back to Warner in 1959, which is you say yes or no with some probability and so forth. Okay, for the epsilon 0 differential privacy, there's a natural values you do. Up to scaling, you just either stay at 0 or you flip. Okay. It's potentially suboptimal in general. This looks reasonable, but it could be suboptimal. In general, you might need more complicated, even for the binary input, you might need more complicated things. For example, in this two-party, Ilya is here, so in the two-party work, they needed an extra label S in their protocol. So maybe you're missing something. So let me go plot, as Kamalika says, what the ROC curve looks like, the false alarm misdetection curve for this randomized response. And bingo, it hits exactly the triangle. Nothing more, nothing less. It's right there. And here's the sharp result from statistics, classical work, that if you have any other mechanism, epsilon privacy, that means it has to be inside this triangle, then it can be simulated from the randomized response. So let me be precise. If you have any other mechanism with output y that is meeting epsilon 0 differential privacy, so it's inside this triangle region, there exists a Markov chain, so there is a way to simulate y from x. Or statistically, there's a joint distribution I can put on x and y such that dxy is a Markov chain. So this is, I'm happy to be here at Berkeley giving a talk on a classical result by a Berkeley legendary statistician Blackwell. So this is Blackwell's 1953 result. Comparison of two experiments where he showed that when, for binary hypothesis testing, when one ROC curve is inside another, then there is strictly degraded. That is, there's a Markov chain relating this. One can be simulated from another. Once you understand it at this level, we can, let's say, go back to the distributed ion computation and simulate the protocol they had with a randomized response. Okay, so that's just as an example. So the binary case works out quite nice. Randomized response is optimal, and furthermore, it is the only one to do. Anything else can be simulated by it, so there's no real reason to do it. Once we understand it, okay, so there is a generalization of this to approximate differential privacy. This time it's not 2 outputs, you need 4 labels. But essentially what's happening is that one of the labels you'll never make an error. With some probability delta you just pass 0 exactly, and with some probability 1 is passed exactly. So those are the 2 extra labels. And with probability 1 minus delta you have 2 labels where you normally flip. Okay, so it's very similar. Delta just gives you that slack to say the truth with probability delta. Okay, same thing. You go plot it, it meets the exact differential privacy region. It's not a triangle anymore, it's this pentagonal shape, and that was the exact one. And again, because of Blackwell's result, if you have any other mechanism, epsilon delta mechanism, you can simulate it from this 4-point mechanism. This is the only one to do, as long as all of this is special for binary inputs. So the query output was just an yes, no question.
Question?
Yes.
So does the black hole result assume a like a two-message mechanism, or
Okay.
it allows also like an interactive?
Okay, so excellent question. So there is no interactive setting in the Blackwell. Okay, so we can come to it. So maybe I shouldn't have put those references. We should have had it an offline discussion. But I know and understand that distributed computation, we have interactions and so forth. But in the Blackwell setting, there's no such thing as interaction. You just have two hypotheses, theta is 0 or 1, or d is d1, d2. And you have a mechanism that you can view it through x or through y. And you go plot the false alarm misdetection probabilities where the curve is one inside another. So there is no notion of any interaction, or it's just a comparing two statistical experiments. There's no operation, no more than just that. Okay, once we understand exactly for binary query outputs what the right mechanisms are, and when I say right, this is the only one. It hits the privacy mechanism, and anything else can be simulated from it. Composition theorems come naturally. They come automatically, because if you have, let's say, two queries now, so it's like vector query, two outputs, and we are doing a worst case over all possible inputs, then if you have any mechanism that's doing whatever you would do, you can always make it less private by going back to the binary one in each case. And so composition, you can just work with composing the randomized mechanisms. Let me do epsilon 0 for now. For two queries, each query you just do randomized response separately, and now you have 4 possible values. Because there's, yes, no here, yes, no here, so there are 4 possible values. So composing two queries is a matter of 4 outputs, 2 input, 4 output, and I even know the exact probabilities. There's a binomial sort of calculation because each one is binary, so in general it's a binomial formula, and you can plot the, again, ROC regions exactly as things compose. And no other mechanisms can be, any other mechanisms can only be sort of inside this. And these give you the sort of the bounds on how much any mechanism, as you compose lots of K mechanisms, so at this point I'm talking with examples where I'm not being interactive. But when you do a converse, you can also do interactively, and there's no harm with it. So you just have to generalize slightly Blackwell's result when you condition on other observations. And if you do epsilon deltas, then you have to compose the pentagons. But you have such strong structure, such combinatorial structure for your mechanisms that it's very straightforward to calculate what the composition region looks like. In 25-minute talk, we can only do so much, but there's a paper, we can look at it. So this is from a region perspective. This is typically not how, for example, papers in the literature are written when you compose queries. Usually you look at, for a given delta, how much epsilon tilde was the end-to-end composition. How do you go from the region to epsilon delta sort of a characterization? Well, delta is just the intercept, and epsilon is the corresponding slope. So that's how you go from the region to epsilon delta. That's why we had this pentagon like this. So this is the e to the epsilon is the slope, e to the negative epsilon is the slope, and the intercept is delta. So for any delta, you take the intercept and look at the slope that contains the curve. So here we have a sort of a binomial structure. I know exactly what my curves look like, and for any delta, I can go take the slope and I calculate it exactly. You can do closed form. You can go do it, and I'm simplifying in the regime of operation. The state-of-the-art results were this. I was in John's talk this morning, and I already noticed that people, this is considered sort of already not there. If you did, then our results say essentially they are the right ones. They are optimal. Up to this logarithm factor. So our results are only sort of better. This is the optimal composition theorem. And the only difference really here is that instead of 1 over delta, I have epsilon tilde by delta. Usually epsilon tilde is this is the dominating factor, epsilon root k. So if you put this as your epsilon tilde, so this basically says that you don't have to pay a price in log 1 over delta. You don't pay even a logarithmic price in delta. Delta could be as much as the same order as your epsilon. up to a constant, then you don't even pay that logarithmic cost. And so at best, you might have a saving of this log factor. So if you ignored it, that's fine. So you can even safely say that you're fine already. Another application of the composition theorem is, for many mechanisms, I can hand compose the mechanisms and see what I get. So I can do this for Laplace, I can do this for staircase, I can do for Gaussian. All these three mechanisms and many more yield the same value. So it's true that the Gaussians ones typically are convolved like this, but that was because it was not as sharp a concentration analysis. The differential privacy constraints give very sharp bounds on the conditional probability distribution all along the moment generating function. So the traditional method for measure concentrations were involving first and second moments, Azumas. But because in this case I have such tight control over the entire moment generating function, I can use sharper concentration theorems. In particular, a Chernoff bound with a carefully tuned parameter, I have such tight control over my moment generating function, so I could use something like Chernoff bound to tightly handle the measures. Once I do that, then you can actually get this kind of from here to here just by doing that kind of a measure. Oh, I'm time. Cynthia said she's loving the talk, so I forgot all about my time. All right, so sorry, I completely skipped here. So you can also do a direct sharp concentration analysis. So our paper is available. Okay, but I really want to go back to the staircase mechanism. What was that all about? Where did this staircase shape come from? I mean, what's happening? And in the community I come from, we really want intuition. I want to understand what's happening. Okay, so for that, binary didn't do it. Binary, everything was already nice. So let's take ternary outputs. Now a query output is 3 possible values. And let's say my neighborhood is every pair. So, okay, so every pair I really want to I want to provide privacy. You could have had other things like this one, only 2 pairs and stuff. But let's say every pair for now. And now now I have 3 diagrams because I have 3 pairs of tests to do. Output 1, output 2, output 1, output 3, output 2, output 3. So 3 tests. So I have to draw sort of 3 curves. And now there is a trade-off. You can hit the triangle fully here, but this one will be very bad. You will be along the 45-degree line. So the diagrams start having a tension between them. You can never be fully use full use of the privacy in all of them. You just can't do that. There's a trade-off. And so all 3 cannot be the full triangular region. In this case 3, but in general this is true definitely even more. And so this is our main result. So I should back off and say, so you could say maybe there is a Blackwell-like theorem for 3 ternary experiments. The answer is no. So if you have a 3-valued 3 hypotheses and you look at the entire 3-dimensional error region and one mechanism dominates another, that's not enough to say Markov chain relationship. Markov chain is much stronger than that. And another legendary Berkeley statistician, Lecam, worked quite a bit on it. There are several conditions, several ways of dominations, but the Markov chain domination is too strong to get for 2 is a very special case of binary input. It was a very special case. But all these ROC curves are within the triangle, so that gives me a handle. So they're not arbitrary curves. And I can say the following. So give me any 3 curves. So that give me a mechanism that I can go plot 3 ROC curves for the 3 different experiments, the 3 hypothesis tests. I can construct a staircase mechanism. I'll define precisely what it is. A staircase mechanism, now is the time to define an abstract staircase mechanism. Previously you had this noise adding in your mind. A staircase mechanism is any probability distribution that can only take on, previously you could take any values as long as they're between e to the epsilon, e to the negative epsilon. But now I'll let them take only 3 values. The ratio can only take on either e to the epsilon or e to the negative epsilon or 1. Only 3 values. It's very combinatorial. I'll call this as my general notions of staircase mechanisms. And for any given mechanism, I can pick one of these staircase mechanisms that will dominate it in a Markov chain sense. Turns out for the special case, and this is true for not just ternary, ternary was an example. This is true for arbitrary inputs. And turns out for the special case where we had this nice structure with sort of lattice integer structure or a real valued structure, and your cost is sort of minimum, there's only one staircase that you get pick. Even though there are many, there's a natural one, and that's the one that's monotonically decreasing. And sort of that's sort of the intuition that goes back to why staircases were the right noise adding, data independent Adam.
So I'm trying to just understand the theorem that's on the slide. So this said that you're saying the theorem is not specific to ternary.
No.
What are the conditions of the theorem?
Okay, so let me be precise. So let's say, I'll be precise about this statement here. So we can do it for ternary. So there are 3 output values for the query, and I can take from there to any number of outputs in the output of the privatization mechanism. So there's a probability transition, that's my mechanism. And this is sort of important that my privacy definitions are on every pair. So for example, if you follow sort of, we can discuss this too. So this is the condition that my privacy, and furthermore it's homogeneous. That means if epsilon 0 on all of them. So it's not epsilon 1, epsilon 2, epsilon 3, things will change. I mean there's a generalization of this, but I'm making homogeneous conditions, and furthermore on every pair. So if you have k query outputs, then you could say there are k choose 2 pairs, and all of them are tightly controlled. Because for every pair I have a epsilon 0 privacy. Yes?
So I wonder what is the relation between this and the universally optimal mechanism, because we don't have a universally optimal mechanism for the case of a ternary input.
That is
Probably there's none.
Probably there's none, yeah.
So you're saying there is a staircase, it's not the staircase.
no, it depends on the mechanism.
Sorry?
So staircase is a family, it's combinatorially defined.
Just the way the theorem is stated.
No, but it says there is a mechanism for which only...
Oh, from an appropriate, from a class. So I'm using staircase mechanism as a class. It's like that's the same sense in which we used it early. There was a parameter gamma. So it's like a class of a mechanism.
Said you meant a family.
So it means a family of...
No, it's stated in English also. So it's,
Also very classic characterization.
Some series for which you can see.
sorry, India?
It's not even a class, it's a characterization of mechanisms, the property of being staircase.
Yeah, you could restrict it, and then it's a class. I think of it as a class, but it's a restriction. It's a combinatorial restriction on what values the probabilities can take.
Does this one again have like a single parameter, like in the one query case?
Actually, let's. It depends on what your utility is again, and that's really another. I want to have our journal paper out before I say that. So why don't I? Later this month we'll have something, and then I'll be happy to share it, and I can see all the precise all details there. I know, yeah, we can answer those things too. Okay, let me summarize. I think I went well over my apologies budget. So we looked at a staircase mechanism, characterization of fundamental mechanisms. We looked at universality in a certain limited sense. It's a cost framework. And with the right intuition, using the operational lens, I can go back and try to understand the universality in a Markov chain framework, so you can simulate things. And yeah, I'm particularly happy. The workshop is at Berkeley. The legendary statisticians Blackwell and LeCam, Berkeley's from Cal. And so yeah, another way to think of the results as sort of converses to Neyman Pearson. In Neyman Pearson, you're given the statistics of the channel and you try to find the best schemes to find false alarm misdetections. Here I give you false alarm misdetection. I try to do the minimum variance or something like that on the channel itself. So if you're going to think of it, you can think of it as a certain converse to Neyman Pearson. Okay, so our papers are online, and this really work with 2 people. My graduate student Chuan Geng, who's actually my graduated student, so let's be precise. Yeah, Chuan is right here. And my colleague Seung Oh, he's also actually as fun to work with as he is on this picture. He'll be here tomorrow. He's at Stanford giving their colloquium talk today. And I really want to acknowledge very helpful discussions. I'm new to this area. Also sort of, yeah, It's completely new, actually. And I've been helped by very generous discussions and comments from Kamalika and Adam, and from Moritz. Thank you so much. Yes.
So I wonder if these techniques can yield impossibility results for data-dependent, universally optimal.
Yeah, I always worry that I don't know the literature enough. What are these impossibility? I know there are some.
So we have for data-independent universally optimal mechanisms, we have some possibility results ruling out almost all queries. The existence of such mechanisms for almost all queries. The one account query is probably the only query that has such a mechanism. Now, but these impossibility results, we have some impossibility results for data-dependent mechanisms, but the general results are only for data-independent mechanisms. So I wonder if this can give us some light into.
I'm sure, except I need to know what this.
Okay, we can discuss offline.
I would love to. I'll be the first to say I have actually very limited. Not out of trying. I mean, I think I keep trying, but it takes a while for me to read. The writing style is quite different, actually. So it takes. I mean, Adam knows all about it. So having straddled different areas, so we had a chat about it. So it's quite somewhat different, but the math is similar. So we'll be happy to chat.
More questions?
Thank you.